Hi everybody. In this video we're going to talk about drug regimen equations. So using the skills that we talked about, or the equations that we talked about in the previous videos on pK constants and concentration equations, let's see how we use those concepts to develop actual drug regimens that we treat patients with. Now often you'll see it called TDM, or therapeutic drug monitoring. And what is really the overall goal of drug regimen equations, or therapeutic drug monitoring in particular? And that's to design, monitor, and adjust. So designing drug regimens for patients, how do we monitor, make sure that we're getting the right levels that we want, and then adjusting. There's two main areas to therapeutic drug equations or drug regimen equations, and that would be a dose or a maintenance dose, including loading doses. And then the other part is interval or frequency. So in order to calculate a drug regimen, we have to calculate a dose or a maintenance dose or loading dose, if that's what we're doing, and an interval or frequency as applicable to that scenario. So let's start to get into these drug regimen equations. So here I've created a table where we'll see where certain equations apply, and this table includes bolus dosing, intermittent infusion, continuous infusion, extravascular, and average steady state scenarios. So on this slide we're going to talk about loading dose and tau. So loading dose and determining the interval. Let's look at the first equation that we're going to see where it applies. That's loading dose equals concentration at steady state that's desired times volume of distribution. And it should be said that the doses come in milligrams generally. So where does this first equation apply? It applies in a bolus situation where instead of saying CSS, generally we call it CSS max. So what is the max concentration we're shooting for? In a continuous infusion, what's that steady state concentration? And then similarly, in an extravascular situation, would be CSS max over that bioavailability that we must account for. And then for average steady state, it's CSS over bioavailability. Let's take a look at the next loading dose equation. And that's equal to the infusion rate constant over 1 minus e to the negative elimination rate constant times the dosing interval. And which scenario does this apply to? Intermittent infusion. And you could probably surmise that because of the incorporation of the infusion rate constant here in the top. Now finally, let's see how we calculate that actual dosing interval tau. And it's calculated by doing the natural log of the concentration at steady state, that's max, minus the natural log of concentration at steady state, min. So what is the range of steady state concentrations that you're shooting for, right? Because in multiple dosing scenarios, so anything but continuous infusion, you're going to have highs and lows to your concentrations. So it's what's really the average we're shooting for. And that's divided by the elimination rate constant. So what scenarios does this apply to? And where it applies is in bolus. Will just be this equation without any other terms being added on. Intermittent infusion, we add a plus t prime to the end, plus t prime here, okay? And then for extravascular, we add in plus t max to the end of the equation. So that's what it looks like when we want to calculate the dosing interval in drug regimen equations, and if we need to calculate a loading dose. Let's take a look at the remaining drug regimen equations, reminding ourselves that dose is always in milligrams. The first equation here, dose equals CSS max times V times 1 minus e to the elimination rate constant times tau. Which scenario is this used for? Bolus. Moving down to the next equation, we have this admittedly more messy equation here. It's CSS max times V over F times 1 minus e to the negative rate elimination constant times tau over e to the negative rate elimination constant times T max. So two things should kind of set off the alarm bells in your head, T max and F. So what scenario would this be used for? extravascular. Continuing down to the third equation, we have CSS times clearance times tau over F, and you can actually convert that into a different form as well as if you substitute out clearance. And what is this used for? Average steady state. So this is one of those special equations where you can really apply it to multiple dosing routes as long as you plug in what the value is for bioavailability. Finally, not everything has a dose, right? Bolus has a dose, extravascular has a dose, but when we're doing infusions, we have to know what is the rate of infusion that we're actually giving the patient. So that's K naught. So how do we calculate K naught? That's CSS times clearance, or CSS times rate elimination constant times volume of distribution. So which scenario does this apply to? This one is for continuous infusion. And then for the last equation, we can see it's somewhat similar except for we have T prime in the equation. So what do we think this applies to? If you have T prime, it applies to intermittent infusion. So here we can see that these are some pretty standard basic equations that have some messy parts to them. There's a lot of similarities in terms of how we calculate loading dose and an interval, and then it gets very specific for how we calculate a dose or an infusion rate for a given drug. Thank you for your attention.